Hello, my name is Martina Formichetti, and today I'm gonna present my dissertation project called Active and Passive Flow Control Concepts for Drag Reduction, Separation, and Weight Control. These concepts have been applied on a simplified car model. What you see in this slide is called a Rover or Windsor model and is the simplified car model that my research uses. This is characterized by a highly curved front region to try and minimize the drag production from this area as much as possible and concentrate on the slant area, which is what you see here. The slant's length is kept constant to about 22 millimeters, while the angle is changed from 0 to 40 degrees to observe the change in wake and drag production. This kind of simplified car model have been widely used before for early stages of flow analysis for car aerodynamics, and even though they're not as accurate as more realistic ones, the loss in accuracy is justified by gaining simplicity for, in this case, a computational domain or for manufacturing for experimental studies. This is the response in the wake for change in slant angle. As you can see, this is 0, 10, 20, 30, and 40 degrees. For the 0 degrees, there's a big wake and is mostly much more symmetrical than the others. For 10 to 20 degrees, we have flow which stays attached until the very end. At 20 degrees, we can start seeing a small separation bubble just here, which is more evident in the 30 degrees one. And then on 40 degrees model, the wakes, the flow separates here, creating a bigger wake, a bit more similar to the 0 degrees configuration, also called square back configuration. This is the response in drag for what we just saw in the wake. This on the left is the graph for the whole model, while this on the right is the graph for the slants only. We can see that the drag starts decreasing from 0 to 10 degrees, achieving the minimum value at about 0.26. And then it starts increasing again until it reaches its peak at 30 degrees at about a value of about 0.32, and then it drops again 35 degrees and 40 degrees, and they have much lower value than at 30 degrees. This is where the wake detaches, the flow detaches, creating a bigger wake as we saw before. And we can see that the slant has a major contribution to the overall drag, as for example the 30 degree value is about 0.2, while the overall value is 0.32 more or less, and this is more than 50% of the overall drag. For drag reduction concepts, so far most of the research is about delaying separation as much as possible. So here we can see this concept by introducing flow control devices in this area. The flow tends to stay attached until this part here and create a very small wake similar to the 10 or 20 degrees wakes, but I'm actually working on drag reduction by promoting separation instead of delaying it, achieving this kind of a bigger wake, more similar to the square back configuration than 10 or 20 degrees, by introducing flow control devices here. The idea is that the vortices will be further away from the model surface, and this will affect it less by and in this way reducing the overall drag. Flow control devices in general can be divided into two categories. This is passive and active flow control devices. Passive ones are usually structural, and the main difference between these two is that passive cannot be switched off, while active can be switched on and off. For passive flow control devices, here we have two examples. On the left is a vortex generator, on the right is a flap. for vortex generators that have never been used before to promote separation. They have only been used for delaying separation, because the way they actually work is they energize the boundary layer by creating concentrated vorticity and making it turbulent, and in this way delaying separation until a later stage. And flap is widely used on aircraft wings, for example, to increase the lift, but so far there's little, if any, research on using these kind of concepts for promoting separation. Active flow control devices are what is called actuators, for example. Most common types are plasma and fluidic, and plasma, for example, they use high voltage alternating current signal that goes through pairs of electrodes, and in this way it energizes, it ionizes the air surrounding it, creating a low temperature plasma, and these molecules of ionized air can be accelerated in an arbitrary direction by an electric field. Here we can see two plasma actuators. In this way, this one, for example, on the right, the induced velocity is opposite to the direction of the flow. So the flow comes in this way, and the induced velocity of the plasma actuator goes that way. And here instead, it goes in the direction of the flow. Plasma actuators have been used before in previous research for delaying separation, but so far have never been used for promoting it. And I'm gonna try and do that in my research. Right, for my research, I decided to use more passive flow control devices than active ones because they're easier to simulate in a computational domain, and therefore I used 4 kinds of passive and just 1 kind of active flow control device. So the first type of passive flow control device that I decided to use is vortex generators. On the right, a more conventional one called pyramid or delta shaped vortex generator, and on the left, bit of a stranger one called bump shaped vortex generator. The most crucial parameter for these kind of devices is the height and the spacing between them. But most importantly, the height. I decided to start with a height of 10 millimeters, and I kept the dimensions consistent between the 2 types to observe the response in the wake. The width is supposed to be 2 times the height, and the length 5 times the height. And this kind of device has never been used before to promote separation, but actually to delay it as much as possible. Second type of passive flow control device that I've used are flaps. On the left, a conventional horizontal flap, and on the right, what is called a gurney flap, and I call streamlined step plane. This is basically a cubic step, and I decided to streamline it to try and introduce the drag while try and control the wake with this little step. The dimensions for the horizontal flap have been taken from previous research, so it's supposed to be about 15 millimeters long and at a 30-degree angle from the slant, so it looks horizontal because we're working on the 30-degree model. While for the streamlined step plane, I try to keep it consistent with the vortex generator, so I gave it a height of 10 millimeters, but there's not much research on these already, so it's been chosen arbitrarily. Plasma actuators are the active flow control devices that I decided to use, and I positioned them on 2 different locations. So one at the roof's edge, trailing edge, and the other one at the slant leading edge. So this one here is horizontal, and this one here is at a 30-degree angle. These have been used both with induced velocity in the direction of the flow and opposite to the direction of the flow to analyze the response of the wake. Moving on to the results, I put this slide here to make it clear that I'm working on the 30-degree model by positioning flow control device on this section here, so the roof's trailing edge. and I'm trying to make the flow detach earlier and achieve a bigger wake, more similar to the square back configuration of the same model. The response and drag, as we saw before in the graph for the whole model and the slant, for the 30-degree configuration we achieved the peak value, which is about 0.32, and for the square back it's much lower, it's about 0.287. So that's what we're trying to achieve. Going on the most promising methods, I'm gonna keep the 30-degree and square back wakes on the left for the next slides for comparison reasons. And so most promising method, as you probably already read, is the plasma actuator. This is very exciting because I tried it both in the direction of the flow and opposite, and it works either way. If it's in the direction of the flow, it keeps the flow attached until this part here, so it delays separation effectively and reduces the drag. If used with induced velocity opposite to the direction of the flow, it makes the flow detach earlier by creating this bigger wake, much more similar to the square back here than the 30 degrees one clear configuration. And the response and drag is impressive. The value is about 0.8, which is even lower than the square back configuration, clear configuration, and this is, I consider this my most successful method so far. Second most promising method is the horizontal flap. The good thing about this one is that it worked. The responses in drag is very impressive as well. Again, below the square back configuration, and the thing about this one is it is very cost effective because it's easier to manufacture and much cheaper than the plasma actuator, even though it's a passive flow control device, so it stays on and it can be switched off. But I consider this a huge success for this research as well. Another feasible method is the streamlined step lane or gurney flap. This one creates a bigger wake, as you can see, and therefore the flow detaches early, but it didn't achieve a very low drag coefficient like the previous two methods. That's why I said feasible instead of most promising. But this one is like the flap, the horizontal flap, is very cost effective because it's just a structural change, and therefore I consider it a success as well. The methods to be further researched are both the vortex generators, as you can see the wake appears bigger and the separation has been induced earlier, but the drag is increased instead of decreased. And this is for the bump shape vortex generator, and same story for the pyramid one, the drag's even higher, and the difference between these two wakes and the ones we saw before for the methods that worked is that the wake is actually pulled down, while the other ones have more of a kind of an reverse S shape. This one is like is pulled down suddenly, and this is probably why the drag increases rather than decreases. Now moving on to the conclusions. We proved that the drag can be reduced by inducing separation instead of delaying it. The most promising methods have been the plasma actuators, and they're very exciting because they work either way to reduce drag, both inducing separation and delaying it by changing the induced velocity direction. The flaps work really well, especially the horizontal one. And for the vortex generators, they work to induce separation and create a bigger wake, but they didn't do much for the drag reduction, and I'd say this is worth researching further to optimize the sizing, spacing, and distance from the separation point. Unfortunately, due to time constraints, it was not possible to do that for this research. Alright, this is all for my presentation, and thank you very much for your attention.